In this video, we are going to overview acid and base chemistry now that we have gone through all of the lectures for this chapter. And I'm going to start just with a definition first, a definition of acids and a definition of bases. So an acid will always donate a hydrogen proton or a hydrogen ion, and a base will always accept one. This is the Bronsted-Lowry definition, and the one that we'll use primarily in this class. And so what it looks like when we have these acid-base reactions is we have, for our acids, we usually have a way of denoting it as HA to generalize it. So you have some acid that has an acidic hydrogen on it, and that hydrogen's right here. And if we add this to a base, and in this situation, I'm going to do water, we're going to end up with H3O plus as one of our products, and A minus, what's left over after we lose that H from our acid. And so that's going to be our acid reaction. For base, a base we usually abbreviate with a B and an extra lone pair. That lone pair is required for something to be a base. It has to accept H plus, which means it needs to have 2 electrons to be able to create a covalent bond to that hydrogen ion. Let's use water as our acid. And what will end up here is we'll snatch one of these hydrogens on the water, and the base will accept it. And so we're going to end up with BH plus. So one of those hydrogens now bonds to the base molecule, plus OH minus. And in this, something that really characterizes acids is the presence of H3O plus in solution. And for bases, it's the presence of hydroxide ions. Now, they're both present in any aqueous solution, but you'll have more H3O plus when it's an acidic solution, and more OH minus when it's a basic solution. Another definition that I want to cover right away is amphoteric. I'll put it down here. And this means something can act as both a base and an acid. And a perfect example of that is water. So something that is amphoteric can both act as a base when it's in the presence of an acid, or act as an acid in the presence of a base. And water is one of these, the one we see the most commonly, but there are other examples of these. Anything that has both lone pairs and a hydrogen would be capable of this. And so another example might be something like H2PO4 minus, something that has oxygen with an extra electron that would easily form a bond to a hydrogen to form H3PO4. Or it has hydrogens that are bonded to oxygens that could easily lose those, like and form something like HPO4 2 minus. And so looking at these basic definitions, though, it can be a struggle for a novice chemist to identify and distinguish between a base and an acid. And so the kind of key things you're looking for when you're trying to decide which is a base and which is an acid in a reaction is that your base has to have a lone pair. And so common bases are going to be things like let's see, OH minus. Anything with an OH or O2 minus, or anything like with an nitrogen that has a lone pair as well, like NH3, are really common bases. An acid is going to be something with a hydrogen it can donate, but lots of things have hydrogens. And so that can be a little tricky. Because we see things like CH4 aren't very good acids, but any of our halogens where we have a hydrogen and bonded to a fluorine or a chlorine or a bromine are all fantastic acids. Also, when that hydrogen is bonded to an oxygen, which is then bonded to something else. So those are what we call oxyacids. So those are kind of our common ones that we'll see over and over again. So thinking more about reactions, the reactions that are shown right here that are generalized, these are dissociation reactions. And a dissociation reaction is just an acid or a base reacting with water. And so if you need to predict the products of these, you will always, if you have identified that you have an acid, you'll always take that hydrogen on the acid and add it to your water and just increase the number of hydrogens by 1 in your product. And if it's a base, it'll take a hydrogen from the water, and so you'll decrease the number of hydrogens on it by 1. And so it's really shuttling just a hydrogen around from one of your reactants to the other, and then trying to determine what the charges are, and that those are your products. So your products should always be different from your reactants by 1 hydrogen. Another type of reaction, though, that we see with acids and base reactions is neutralization. Which is the same principle as our dissociation reaction, except we don't have water guaranteed as one of our reactants. Instead, we're going to bring together an acid and a base, and we'll form typically a salt and water, although not always. So an example of one like this would be HCl plus NaOH, forming sodium chloride plus water, H2O. And it's the same principle of just shuttling a hydrogen around. Here, the hydrogen on the chlorine is going to form a bond with the OH, and that's going to produce our water. Remember that back in chapter 3, we learned about ionic compounds, and so we know that this sodium hydroxide, if it's in water, really represents a sodium ion plus a hydroxide ion, and they're not actually connected to one another. They're surrounded by water molecules instead. Although we can always have neutralization reactions that occur that do not actually produce water, and that's going to be when you see things reacting with, let's take hydrochloric acid again, with ammonium, which is a base because it's got this lone pair on nitrogen. And when these react, we're going to see, again, the basic principle of all of these reactions is the hydrogen on the acid joins the base and forms a bond to the lone pair. And so that's going to leave us with NH4 plus and Cl minus. And so we haven't produced water, but we have produced a salt. We could rewrite this and say it's NH4Cl. It's aqueous, and that's actually an ionic compound. Let's look at the strength of acids and bases. When we evaluate strength, we actually evaluate 2 different things that are really similar, and so it's sometimes a subtle thing to separate them. So when we talk about strength, we think about how strong an acid is, or base, and how dangerous it is. We measure these separately. And one of them, so for strength, we're going to measure that with Ka, which is a measure of equilibrium. It's an equilibrium constant, similar to what we learned about in chapter 6. It's the same one. There's a subscript A to let you know we're talking about an acid, but that's about it. And so our Ka value is really connected to this acid dissociation reaction right here, where our K is going to be equal to the concentration of our products. And for our acid dissociation reactions, one of those will always be H3O plus over our reactants, and we don't include water because it's technically the liquid phase rather than the aqueous phase. There's just a ton of it around, and so it's hard to track its concentration changes. Or you can think of it as always being a 1. And so calculating Ka is going to tell you how far equilibrium lies to the product side. If Ka is greater than 1, it's a strong acid. And if K is less than 1, it's a weak one. And so strength, how strong it is, really just means how many of the acid to hydrogen bonds break. In water. And so a strong acid will have all of those bonds break and form the concentration that of H3O plus that forms will equal whatever the initial concentration of the HA was. So let's write this over here. So again, that means that whatever concentration of the acid I have, it's all gonna break apart, and that will equal the concentration of H3O plus in the solution. We can measure the same thing for a base, which will be Kb, which will be the hydroxide ion concentration because that's our product, and Hb plus, all divided by B, the concentration. And so we can track both of these, and this will track the strength of a base. And so strength we usually immediately think of as, oh, well, a strong acid is therefore dangerous. Well, a strong acid at a very small concentration is not actually that dangerous. You have essentially strong acid in your stomach, it's hydrochloric acid. But it's the concentration that tells us how dangerous it is. And so we actually track that with the pH scale. And the pH scale is a measure of the concentration of H3O plus in solution. And so this is really just how concentrated that acid concentration actually is. And so as this increases, we see the pH decrease because pH is going to be equal to the negative log of the concentration of our H3O plus. This just means that we're measuring our H3O plus concentration on a logarithmic scale, which is one way to assess a value for something that has a lot less zeros, or times 10 to the negative something exponent or positive exponent. And this scale is typically 0 to 14, but it can go higher than 14 or lower than 0. And we know that a pH less than 7 is acidic. A pH equal to 7 is neutral. And a pH greater than 7 is basic. And so if we have a weak acid with a very low pH, I would consider that more dangerous than a strong acid with only a moderately low pH. So I'd like to circle back to our idea of amphoteric again, as we evaluate both, highlight this, as we evaluate Ka and pH. And so something that's going to be amphoteric, like water, is going to allow us to kind of convert between the way of looking at strength and how dangerous something is for an acid versus a base. So for our bases, we had a Kb or a Kb to replace the Ka. Similarly, with pH, we also have POH, which is equal to that negative log of the concentration of the hydroxide ion. And here, our POH is less than 7, then it's very basic. And so it's the opposite of what you measure with pH, because it's measuring hydroxide ion concentration instead of hydronium ion concentration. And we can convert in between these two. And we can do that with a couple of equations that are based on water and the autoionization of water from it being amphoteric. And so one is that Kw is equal to Ka times Kb. And also the pKw is going to be equal to the pH plus the POH. And so what that essentially gives us then is 14 is equal to pH plus POH. That Kw value is equal to, so let's build this off right here, 1 times 10 to the negative 14th. It's going to allow us to interconvert between those two, which is pretty useful. So applying acids and bases, you'll see these in your household, of course, all over the place. Especially if you go into the medical field, we have acids and bases that we have to manage because our body is aqueous, and so we need to maintain a pretty specific pH. So some of the applications of this work is thinking about titrations, which is how you measure the exact concentration of an acid by adding a known amount of a base, let's say, until you neutralize it completely. But then also the construction of buffer systems or buffer solutions. And so buffer solutions is what I chose to focus on with this quarter. And as I think it applies quite a bit to taking lessons from this class into biology and into anatomy and physiology and into an allied health field career. So a buffer solution is defined as having a weak acid plus its conjugate base. And so an example of a weak acid, off the top of my head, would be something like, let's see, HPO4. Okay, let's just mean it's not amphoteric. Acetic acid, where we have a fairly good size organic molecule and with one hydrogen that's acidic. And so it's a weak acid, and its conjugate base is going to be whatever the molecule is without that hydrogen. So the conjugate base is what exists after you have broken the bond to the acidic hydrogen. And so in this case, it's C2H3O2 minus. Coming back over to our dissociation reactions, we can identify the conjugate acid and the conjugate base. So I have, for my acid reaction, I have an acid reacting with water acting as a base, and my acid will always produce a conjugate base. And a conjugate base is just a base. H3O plus can act as a base. It has a hydrogen it can donate. It's unlikely that it'll accept a hydrogen, so it won't act as an acid. And the conjugate word just means it's the product. And so because it's on the right-hand side of that equation, it's the conjugate base. The A minus that's left over after the acid loses its hydrogen is the conjugate base. It can accept a hydrogen now, so it's a base. So for our base dissociation reaction, we have our base, and now water is acting as an acid. And so our HB plus is the conjugate acid of our base. It accepted a hydrogen, and now it can act as an acid, while our hydroxide is the conjugate base. And so buffers are always going to be acid and conjugate base pairs. Typically, the conjugate base will be a salt, since it'll be an ion. So I would pair it with something like sodium or lithium or potassium, like this. And when you have both of these around in solution, then you can have an acid or a base react with it. And so its job is to both neutralize acids and bases that are added using the same neutralization reaction that we just talked about here. And having both the acid and the base in solution in roughly equal amounts means that if an acid is added, it'll react with one of those two components to be neutralized. It'll react with the conjugate base to form the weak acid. And that's kind of the interesting thing with this. So if I add acid to my buffer, it'll react with the conjugate base in my buffer, and it will produce the weak acid of my buffer, plus the conjugate base of my acid. And so it's a way of taking a strong acid and converting it into an acid that's already present in solution. And that's how it does its real job, which is, or its main job, I guess, the essence of it, which is maintain a pH for a system so it doesn't change dramatically. And so let's take our example again for our buffer system. If I added a strong acid like hydrochloric acid, it would react with the conjugate base in my buffer solution to form that weak acid of my buffer solution. And then I would have some chloride ions left over. What we see here is that hydrogen on the strong acid is coming over to the base to produce the conjugate acid of our weak base, or the weak acid of our buffer system. So anything that's added to it is just going to get converted into one of the two species of the buffer system. And that's how it maintains pH within a pretty narrow range at times.